since 2021 a professor at Regensburg for databases with a research focus on moving object databases, and he will give his talk on design and implementation of high-performance domain name services at commodity hardware. So, yeah, we're looking forward.
Thank you very much for the introduction. Hello everyone. I'm happy to present the work Design and Implementation of a High-Performance Domain Name Service on commodity hardware today. So first a few words about the domain name system, so everybody knows what I'm talking about. The Internet Domain Name System is a large hierarchical distributed database that's used to look up public information associated with domain names. So for example, if you type into your browser www.somerset.eu, then your browser cannot directly contact the web server, but has to ask the DNS resolver at your provider to retrieve the information, the IP address of the web server, gets back the response, and after that can retrieve the web pages from the web server. And that's of course not the only purpose of the domain name system. Also to look up mail servers, that serves is responsible for mail addresses of a specific domain, anti-spam information, zip endpoints for IP telephony, and so on, and much more. And the information looks like this. On the left side we have actual domain names. In the third column we have record types, so name server responsible for domains, address records to translate into IP addresses, MX records to specify which mail servers are responsible, and here at the bottom anti-spam information. And that's a textual representation for information that can be associated with domains. So the estimated amount of data globally stored in the DNS can only be estimated. Domain names registered about 360 million worldwide, and average DNS records per domain name 10 to 20. Cannot tell for sure because the system is very decentrally administered, and domain records cannot be enumerated in general. So this is just a rough estimation, about 4 to 7 billion records. So quite a large amount of information, and high availability of this information is crucial, so all services can be reached without interruption. This is a quick sketch of the hierarchy. At the top we have a set of 13 logical root name servers. In reality it's much more physical root name servers due to anycast technology. So the root name servers contain information how to reach the TLD name servers, responsible for the DE domain, com, app, and all other top-level domains. And these in turn have the information where the actual second-level domains that you can register as a private person or as a company are located. And of course, not every domain has its own name server, but usually they are collocated on a single name server. So example.de and example.com can be on a single name server, and much more. This is the typical hierarchy levels, the 3 levels, but in theory much more levels are possible because you can further subdelegate under each domain. So what actually happens if your browser asks for www.example.com is that first the resolver asks the root name server, what's the address? The root name server says, I'm not really responsible for that domain. Please ask .com, TLD name server. Then the resolver asks this one, and the TLD name server says, I'm also not responsible. Please ask example.com domain name server together with the addresses how to contact these name servers, of course. And finally, this name server here below is responsible for the domain and tells us www has this address record, and the browser can contact the web server. So, of course, these 2 steps do not have to be performed all the time. It can be cached by the resolver for a specific amount of time, but from time to time it will happen that way. So, a lot of things have to work until you finally get the web pages of a specific domain name. So DNS servers are critical infrastructure. If they fail, then many services are not available. For example, you cannot send mails, you cannot retrieve web pages, and so on. So we need some strategies for high availability. And one strategy is to not only have a single name server, but many of them. We have seen root name servers, there are really a lot of them worldwide deployed. Also the TLD name servers, of course, are highly redundant because if, for example, the DE zone cannot resolve anymore because then it fails fatally, then about 60 million domains together with their services are not available anymore. But also for the second level domains, usually at minimum 2 to 4 name servers are deployed because, well, depending on the criticality. So if it's a very critical company domain, there may also be a lot more names that are responsible for it. Typical attack on the domain name system are DNS request flood attacks, which means that an attacker tries to overload the system to not be able to answer legitimate queries anymore by having a lot of queries for some domain names in order to overload the server processing power. Traffic filtering on DNS on the network can be used against that. You try to distinguish between legitimate and illegitimate queries and then filter out the illegitimate ones. And finally, we can use caches between the resolver and the actual name servers that caches information. So if a domain is asked over and over again, it takes the load from the actual name server and the cache can answer this query instead. So we're safe. Now let me introduce to Mallory, because a skillful attacker can overcome these strategies, and Mallory is such a skillful attacker and laughs at our efforts on mitigating her attacks. Redundant name servers, of course, she can attack all the name servers responsible for a domain. Remember, all information is publicly available, which name servers are responsible for a domain. Traffic filtering on network or DNS request floods can also be circumvented by crafting packets that simply cannot be distinguished from legitimate queries. That's possible if you do it the right way. And the caches are also only useful if for a specific domain the same information is asked again and again. So if you simply ask for different domain names, different types of records and so on, a cache will not help you here anymore. And so the idea is the strategy that the name server simply answer to all queries that it receives over the network. So we try to shift the bottleneck from the processing power of the server to the available network bandwidth. In the actual case, we had a 10 gigabit per second server, so that was the bandwidth to the internet, and with the standard name server software, PowerDNS with MySQL backend, the common setup, it was far from being able to separate this network bandwidth. Several 10,000 packets per second were enough to overload the server, and the goal was to saturate the outgoing network interface to answer all queries that are incoming. And these design concepts helped with that. First, we divided the system into a high-speed data plane and control plane. That's a concept perhaps familiar from internet routers or internet switches. We have a control plane that manages some forwarding information base, and a data plane that quickly fetches packets from one port and uses this forwarding information base to move them as fast as possible to an outgoing interface and so on. And a similar concept was applied here. We of course need a very efficient data structure for fast lookup of the information, similar to the forwarding information base, an in-memory tree that is based on a radix tree that supports the fast lookup of these domain names. Finally, in advanced preparation of DNS answer packets, so the answers that can be sent out on the network should be as readily available as possible. So not fetch them from secondary sources, but immediately in memory available here. And TCP-based queries become more and more important. I'll tell about that a bit later. So TCP is a very powerful, but also we need very much effort for applying this protocol. So we need to find a solution for that to also have TCP-based queries answered efficiently. And with this concept, it was possible to saturate such a 10 gigabit per second link under worst case conditions with quite inexpensive hardware, which totals about €500 excluding that. So first point, data plane versus control plane. This is a very high level architecture schema. In the middle we have the common data structure which contains all the DNS information. On the left side we have the data plane that only reads this in-memory database. It receives queries from the internet, parses them, looks them up as fast as possible and sends out the queries again. And on the right side there's a control plane that configures, populates and updates this in-memory database, and also provides the user interface to administer the server, retrieve statistics, set operational parameters, and so on. So the data plane was implemented using the data plane development kit that was introduced by Intel, I believe, and is now an independent open source project, pdk.org. And this framework provides direct NIC access, so the process can access the network interface card from user space and doesn't have to go through the OS network stack. On the other hand, this also has its drawbacks. We need to implement all network layers up to layer 2, the Ethernet layer, because operating system servers cannot be used and the NIC cannot be shared with other processes, so it's exclusively for the name server process now. Data plane has fast read-only access to the DNS information tree and avoids all blocking operations during its normal operation. The control plane, on the other hand, uses the standardized networking stack to provide administrative interfaces like web interface, REST APIs, and so on to administrate the server, configures the operational parameters like listen addresses and so on which addresses should our name server answer queries, and provides a read-write interface to the DNS information tree to populate it in the first place from secondary sources and also to update the records if DNS information changes. And all things that are performed by the control plane are not considered time critical, so you may have to wait a bit until updates are performed and so on. This is a very quick sketch of the DNS information tree. And on the top, if you look closely, you see that the domain names are stored backwards here. And that's because, so this is ple.com here at the top. And the reason is that in domain names, the last parts are the one that are top of the hierarchy. So www.example.com is TLD, example is the second level domain, and at the third level we have www. So all is stored backwards, and the next character then decides if the next character of the query domain name is an A, we go to the right side and are left with srv.maple.com. If it's an M, then we're on the left side at ample.com, and then if the next character is an S, then we have www.sample.com in total, or example.com if it's an X. And the leaves of the tree are the actual record information that is asked for. Yeah, so it's the central element, access read-only from the data plane, read-write from the control plane, modified radix tree, and it contains records for all served domains already in memory. So after startup of the server, nothing should be fetched from secondary memory at query time. It's designed for one-pass traversal, so a single traversal of the tree has to be sufficient to answer a specific query. That's important if a domain name cannot be found, but things like wildcard records and so on are implemented, then domain names far up in the tree can become relevant then. Also, there are technical details like CNAME referrals which point to other parts of the tree and pointers to these tree parts are maintained, so we do not have to search for these explicitly, but we can simply follow a pointer and get the relevant information. And this tree is built and maintained only by the control plane, either from a relational database that's read or from zone files like bind, the standard name server uses by default zone files, can also be updated via network APIs, via REST interface, or from Lua scripts that are executed if you need a higher level of dynamic maintenance of this tree. Let's have a look at the records. So we've seen this is the textual representation of such a DNS record, and this textual representation is only used in the secondary storages like zone files and relational databases, but actually on wire we have different binary format. This binary format is defined by RFC 1035 and is different for each record type. See, on the left side we see a sketch for an X record, for a mail server record, and this is the binary protocol data that should be sent out. So you see already the name here is not a simple string, but a label format with length bytes, and then the label parts, next length byte, next label part, and so on. And possible but not very efficient strategy that is, for example, employed by PowerDNS with the MySQL backend is we wait for a request on the network, then we fetch the dataset from the database, convert it to on-wire format, and send the answer packet. But of course, we try to keep as much work away at query time. We want to do that all in advance. So the actually implemented strategy is to, in the control plane, that's what the CP here means, we fetch all records, build the DNS information tree, and build already also the on-wire buffer for all of these records. in advance. And then at query time, we only have to wait for the request, traverse the tree, and take the binary DNS protocol data that's stored in the leaves and send out this bundle immediately. This is of course time-memory trade-off. Such a string has much fewer data than the tree plus the protocol data. So per record we have to count about 1.1 kilobyte in average, depending on the actual record of course. So last building point, last puzzle piece is TCP requests. DNS is by default packet-based, with UDP packets, so it's stateless. We have one request packet and we send out one response packet. But the maximum allowed UDP payload is 512 bytes. It's more if you use eDNS0, extended DNS, but still it's limited, and DNS answers are often much larger today, especially when DNSSEC is employed, because then every record is signed and these signatures take their space. So stream-based answers are fallen back to if the answer is too large for a single UDP buffer, and so TCP is more and more needed for the requests. Quick overview, TCP is a stateful protocol where we have connection tracking. So here the three-way handshake establishes such a connection, and then we have an entry in our operating system connection table. Then the data exchange phase follows, and after that the connection is shut down again. And the state machine for it is quite complex, and the RAM usage might get very high under attack conditions, or connections have to be dropped. Or also for a single packet to look up the correct connection if the connection table is very full, can be quite a lot of effort. We, on the other hand, have some benefits from TCP. It prohibits spoofing, IP spoofing. We have reliable data transfer with automatic retransmits and much more. But these are things, since UDP is the default and UDP doesn't have all these things too. So we do not really need that. If we drop these benefits, then we have the same level of service as we have with UDP. So the idea is to implement a status TCP for DNS requests. So each time we receive a SYN, which says, I want to build a connection, we simply send out a SYN ACK and say we accept this connection, but we don't really make an entry in some table because we're trying to be completely stainless. If we receive